And then, so last time we were talking about virtual machines. We had an introduction to virtual machines. We looked at a classification of virtual machines. Let me just step back a few slides. We talked about process VMs and system VMs. And we also, talked about different types of process VMs, different type of system VMs, and within that we looked at what is the difference. We looked at the interface level classification, how process VMs virtualize ABI, such as system call plus userize interface. System VMs, they virtualize the instruction set architecture to provide a whole machine view of the system to the virtual machines. So our focus was mainly on system VMs, and today we're going to get deeper into system VMs to understand how individual resources are virtualized. Okay, were there any questions from the previous class that anyone wants to ask right now? Anything that wasn't clear, or anything you want me to go over? Okay, so now we're going to talk about virtualizing individual resources within a system VM. We're going to put aside process VMs for now and focus on system VMs. So there are three types of resources in any machine: CPU, memory, and I/O, right? So so we're going to first, so whenever we are providing a system virtual machine, the underlying hypervisor has to provide a virtualized view of all these three resources: CPU, memory, and I/O devices. So first we look at CPU virtualization. So what this means is that every VM would see a virtual one or more virtual CPUs. So by virtual, just like when you start a process, you get you can create one or more threads. Similarly, for a virtual machine, when you start a virtual machine, you get one or more virtual CPUs. And these virtual CPUs should more or less look just like a physical CPUs. They should have similar properties as physical CPUs. They should be discoverable by the operating system, the guest operating system in the VM. They should be discoverable by the guest OS, and guest OS should be able to manipulate them and control these virtual CPUs just like a regular physical CPU. So we want to maintain as much of the physical properties as possible in these virtual CPU abstraction. So for example, you may start a VM and then you may say, okay, there are maybe 4 virtual CPUs or 8 virtual CPUs. In some cases, you can even specify the NUMA topology. What that means is like, you can sometimes buy computers with multiple sockets, and each socket has multiple cores, right? And then some of them have local memory, and which are then, they talk over a NUMA architecture, non-uniform memory architecture. So you can similarly create a virtual NUMA topology and provide that to the virtual machine. So, so whatever properties are there for physical CPUs, these can be reflected for a system virtual machine. So what do the hypervisors do? So when the virtual machine starts running, and then it sees these physical CPUs, it would start creating processes and scheduling processes on these virtual CPUs. But then as the guest OS tries to perform such a certain privileged operations, then on the virtual CPU, it will trap. And those privilege instructions will trap to the underlying hypervisor. Hypervisor would then emulate those privileged operations on behalf of the virtual CPUs. So before Intel and AMD started providing hardware support for virtualization, so these traps and emulation operations were very expensive. right? So what that meant was that a lot of operations would trap into the hypervisor, and hypervisor would have to play a lot of tricks to have the corresponding effect on the physical CPUs. But then, of course, Intel and AMD realized the value in providing hardware support. So since then, in over the last 15 years or so, both Intel and AMD have provided tremendous functionality. They have added tremendous functionality. Almost, they have re-architected the entire, execution architecture around this virtualization subsystem. So in Intel's case, for example, there is a standard called VTX, which VTX stands for Virtualization Technology Extensions, I believe. So, so what that means is that CPU comes with every CPU that you buy these days. It has VTX capability. What that means is it has some additional optimizations, additional features that allow virtual machines to execute faster, right? And specifically, VTX deals with CPU virtualization features, and we'll talk about what these are. Likewise, AMD, which is Intel's competitor, but still works on the same ISA, x86 ISA, it came up with its own extension called AMD-V. And these are pretty standard. And more recently, ARM processor, which has become very popular in embedded systems and mobile devices, it has also started providing hypervisor support. Okay, so the point is that hardware device vendors, or processor vendors particularly, are adding virtualization support in their CPUs. And these can now be used by the operating systems or hypervisors to make more efficient, to provide more efficient virtualization. So as I mentioned a little bit earlier, all this all this hardware support is mainly to make it easier to emulate privileged instructions. So this way a hypervisor can specify what kind of instructions it wants to trap and emulate and what it doesn't want to trap and emulate. And also it provides additional support for virtual memory operations, and we'll talk about virtual memory extensions in a little bit. That's also part of VDX. But as far as CPU virtualization is concerned, we're talking about more efficient way to trap and emulate privileged operations. Okay, so I'm going to talk a little more about what it means to trap and emulate. So, all right, any questions so far before I proceed further? Okay, anything that's not clear, just feel free to interrupt me and ask. Okay. So here's an example. All right. For example, what is a privileged instruction and how does the hypervisor handle? Oftentimes, like the operating system, the guest operating system that's running inside the VM, it may need to execute instructions such as simple things like, changing the privilege level of the CPU. So, for example, a user level process may make a system call, and the system call changes the privilege level of the CPU. Under certain circumstances, the hypervisor may want to trap this operation, okay, and do something with it. Or if it doesn't want to do that, it can also ignore the operation. But if it chooses to trap the operation, then the control transfer has to happen from the virtual machine into the hypervisor. So for example, here we have an instruction, for example, this load program status word LPSW. It's a hypothetical instruction, that that changes the privilege level. Program status word has a bunch of states relating to the execution state of this processor. So when a load program status word basically says load a new state into the program status word register. So this is typically the way you would change the privilege level of a CPU, like the ring 0, ring 1, ring 2, and 3 that we discussed earlier for x86 processors. In order to change that, you would on x86 processors, that's called an E-flags register, but you could, generic name for that is program status word. So when an execution context switch happens, for example, and you have to, guest OS has to change this instruction, it would execute the instruction, but then the hardware will realize that this is a privileged instruction, and it would raise a trap. And what the trap would do is it would transfer control to the virtual machine monitor or the hypervisor's code. And in the hypervisor's code, there is a dispatcher routine. Dispatcher routine is like the first entry point into the hypervisor that will examine what instruction caused this trap. So as you can see in this other figure, a dispatcher would examine the instruction that's causing the trap, and then based on the instruction, it would call one of the several interpreter routines. What that means is that, for different privilege instructions, there may be different trap handlers that would emulate the effect of the corresponding instruction. So in this case, the dispatcher code looks at the instruction and it sees that it's the LPSW instruction, and then it would then jump to another routine in its own code that would then emulate the effect of that instruction on the underlying physical CPU. Okay. And once that's done, then it would finally return back to the virtual machine. And in the virtual machine, it would jump to the next target, which is the target of the program status word LPSW instruction. So in a normal physical machine, there would be a direct flow of control, and LPSW would result in a jump to the other instruction. But because now we are running in a virtual machine, we have to go through an emulated environment. Okay? So another more concrete example is, for example, on a physical computer, when a CPU has nothing to do, it idles. It's called an idle CPU, right? You have no processes ready to run. The CPU has no work. So what does it do? It idles. Idles. What does an idle CPU mean? Usually, it means that it's an opportunity for the hardware to save some power. So it would, when an idle CPU would be put in a low power state where it would do nothing. Basically, it's literally sleeping, doing nothing, and consuming almost no power. There are many different powerless sleep states. And whenever there's something to do, then the CPU would wake up from its low power state and then get back to the OS, and the OS can schedule something. So that's what happens on a physical CPU. But in a virtual CPU, let's say you're in a virtual machine and there's a virtual CPU, the guest operating system still thinks that this is a physical CPU, although it's a virtual representation of a CPU, right? And it can try to execute a halt instruction, HLT instruction. HLT instruction says, my CPU is idle, send it down to low power state, okay? So if this was a HLT instruction which idles the CPU, then, well, it doesn't make sense to idle a virtual CPU because that's just a software abstraction, because the underlying hypervisor may have other work to do. This particular VM has nothing to do, but then the hypervisor may have some other work to do. So as a result, the halt instruction is now a privileged instruction. You want to pretend that the virtual CPU for this VM is being idled, but in fact, the hypervisor may have other plans for the physical CPU. So as a result, the halt instruction would cause a trap, and the dispatcher would send this to a routine which emulates the effect of halt instruction. It would pretend that the virtual CPU has been halted, whereas actually the physical CPU could be switched to another VM to do something else, right? So, and once the guest OS has to be woken up to do some work, at that point you would jump back, return back to the guest OS and wake up this virtual CPU, which was never halted in the first place. So, so this is another example, all right? Where you have emulation. So there are lots and lots of different instructions that are emulated, and that's why you see all these different interpreter routines mentioned here. The basic idea is that the guest OS does something which must be interpreted on the physical resource. Okay. I would request to keep yourself muted so that we don't have echoes or background noise. If you have questions, of course, feel free to ask. So anyone has questions about how trap and emulate works? All right. If you have your microphone unmuted, please mute yourself because we are hearing echo back. Okay. So, so I'm going to proceed further. There's another concept that is worth, I'm sorry, I'm just having some issues with the interface here. So I'll just get back to you in a minute. Okay, sorry about that. So, so another issue to consider is, how does a hypervisor maintain control of the underlying resource? I believe we possibly talked about this in our very first class when we talked about what an operating system does and how its code can be invoked and so forth. So a hypervisor is just like an operating system. It's an operating system for operating systems. So it has to maintain control over the underlying hardware resources. And one of the ways it does that, at least for the CPU, is to maintain control over the timer resource. Timer chip in the hardware basically is used to deliver timer interrupts to keep track of the time. And control over the timer interrupt is really important because all operations in the guest OS depend upon the timing information generated from the timer chip. So, for example, if your process is running too long, it has to be preempted. Then a timer interrupt will tell the hypervisor that maybe it's time to revisit your scheduling decision. Maybe it's time to run another process. So, likewise, a hypervisor, just like an operating system running on bare metal, needs control of the timer. Similarly, hypervisor needs control of the timer as well. So here's an example which shows how a hypervisor might switch the CPU from one virtual machine to another virtual machine. So here you have the first VM in this picture, first VM running in the CPU, on a CPU. And then at some point, a timer interrupt occurs. At this point, the hypervisor would save the state of the previous virtual machine, meaning it would take the execution state, registers, program counter, everything. It would save it in some region specific to the VM, and then it would then run a scheduling algorithm to determine which is the next VM to run, whether there are other VMs waiting, which is the next VM to run. and then it would determine, okay, how long should the next VM run? And if it does so, then it will set up a next timer interrupt. It can program that, since hypervisor has control over the timer interrupt, it can program the timer chip and maybe it will say, okay, let this VM run for another 10 milliseconds or 100 milliseconds. And once that is done, it has to restore the state of the next VM. So the next VM, in order for it to run, its register state, program counter, everything has to be installed on the CPU. So hypervisor would do that, and then it would then give control over to the next VM. It would do a privilege level transition into the next VM, when the next VM would start to run. Okay, so this looks almost exactly like how an operating system would switch from one process to another process. So if you just replace VM by a process and VMM, or the hypervisor, by an OS, then the whole diagram would still make sense. Okay, so this is just to emphasize this point that a hypervisor needs control of the timer chip, just like an OS needs control of the timer chip. Okay, any questions on this so far? All right. So, so I just want to mention one more thing, and I think it possibly got somehow I didn't have a slide for that, but as part of CPU virtualization, let me just go back here. As part of CPU virtualization, we are also one important part is to have additional privilege levels, additional execution privilege levels for the VM. So on Intel CPUs particularly, we have so on Intel CPUs particularly, what VTX and AMD we provide is an execution mode, an orthogonal execution mode called root and non-root mode. So I will just try to write something here to explain what I'm saying. So normally on a normal virtual machine, the execution privilege levels, normal physical machine, the traditional execution privilege levels are 0, 1, 2, and 3, right? And where 0 is where the operating system runs, and 3 is where the user applications run, right? But now when we have a hypervisor is more privileged than the operating system, right? So one of the models that we could have is, since there are 4 privilege levels, 1 and 2 are traditionally unused, you could move, you could kind of move, you could have a model where, you in level 0, you could have hypervisor, and then level 1 or 2, you can have the OS, and level 3, you can have user level applications. This, in theory, this is possible, but in practice, what happens is, if you take existing operating systems that were used to running in level 0 earlier, but then if you now ask them to run in level 1 or 2, they break. Okay, surprisingly, they will break, because on Intel processors, level 0 is not exactly the same as levels 1 and 2. There are levels 1 and 2 have certain different behaviors that we won't go into right now, that make it impossible for traditional operating systems to run in levels 1 and 2 safely. And actually, they will have incorrect behavior. So this was a huge problem in early virtualization systems like VMware. One of the reasons VMware succeeded in becoming a market leader in virtualization was they figured out how to make this work. Nobody else could do that. VMware could figure out how to make this work. We talked about 70% efficiency. So they figured out how to have this 0-1-3 model and have their virtual machines run on x86 systems. But this was not ideal. It was still very costly. There were about like 30% performance hit. So, and the way to solve this was, the solution really had to come from device vendors. So device vendors being, Intel and AMD. So that's where, the VTX and AMD-V interfaces came along. So what the new model was that, when Intel and AMD made changes to their chips, to their processor architecture, they said, all right, we want the operating systems to follow this 0-3 model that they're used to, so that they don't break, right? And in order that they don't break, their execution levels don't break, we are going to provide 2 additional levels of privileges. So they introduced 2 orthogonal privilege levels. These were called root mode and non-root mode. So this is not the same as root user that you get in a Unix system and normal user. This has nothing to do with Unix root mechanism, right? So these are processor level, hardware level, privilege level. So what this means is when you run a hypervisor, so hypervisor runs in the root mode, and the guest OS plus applications run in the non-root mode, all right? And within each of these root mode and each of the and non-root mode, you can have the traditional 0, 1, 2, 3 privilege levels. So in effect, you have 8 privilege levels: 0, 1 to 3 in root mode and 0, 1 to 3 in non-root mode, right? So your guest OS would be running in level 0 in non-root mode, and applications would be running in level 3 in non-root mode. So this way, guest operating systems won't break. So they're still running in level 0, except that they're deprivileged at another orthogonal level, which is in non-root mode. Okay. Does this make sense? I see there's a question. If the VM runs as a process on top of the hypervisor OS, does the whole guest OS get blocked when one process makes a blocking system call? How does the hypervisor provide process level granularity inside the guest OS? Yeah, so yeah, I think we alluded to this a little bit in the previous lecture, where we talked about how virtual CPUs for a guest OS are like threads within a process. So let's say you start a VM, and in the root mode of the hypervisor, that VM would be running in level 3, right? As a process, and within that process, let's say you assign the VM with 4 virtual CPUs, then for each of the virtual CPUs there will be a thread within that process. Now, when you turn that process with these 4 threads into a VM, all of those 4 threads would enter the non-root mode, right? So from root mode, the process which was originally in root mode, which it will now become a non-root mode process. So whenever the process is running inside the guest OS, inside the VM mode, it will be in non-root mode, and those 4 threads in that process would now look like 4 virtual CPUs. Okay, And if any of those threads block, then only that thread blocks, and the other threads continue to execute. So there's so just like, you know, if you're in a physical machine, if you have 4 physical CPUs, if one of the physical CPUs becomes idle or is blocked for something, then, you know, the other physical CPUs can continue to run processes. So the same abstraction applies to virtual machines also. Okay, so I guess your question boils down to, if one virtual CPU blocks, do other virtual CPUs also have to block? No, the other virtual CPUs can continue executing. It's not a problem, right? It leads to other low-level design issues in the hypervisor. For example, you know, I'm not sure if I should go into that much detail, but, you know, these physical CPUs on a physical computer, physical CPUs talk to each other. They can send interrupts to each other, called IPIs, interprocessor interrupts. And but then if you have virtual CPUs, and at the physical level, then IPIs are no problem, right? You know, all the physical CPUs are always there. If one physical CPU sends an IPI to another physical CPU, the other CPU is there to receive it. But then, you know, for virtual CPUs, you might have the case that one virtual CPU may be blocked while the others are running. So what if you send an IPI to a virtual CPU that's blocked? So that's where hypervisor comes in. It has to emulate the effect of the corresponding IPI, which slows things down. So that's another part of CPU virtualization that I haven't necessarily covered here. Maybe a bit too much detail for right now, but it's kind of a long answer to your question. Does that help? Okay. Any other questions so far? Okay. So next we will look at memory. So we looked at CPU virtualization, and now the other major resource is memory. So in virtual memory that we covered earlier, we talked about the notion of a virtual address space and how page tables are used to convert the virtual address of a process to physical address, right? So this is traditional virtual memory shown in this picture. In the normal virtual address, whenever processes run, they issue a virtual address, and every process has a page table, and the MMU looks into the page table and converts each virtual address to a physical address, which is then used to access the main memory for the process. So this is a one-level translation, right? There's one page table. You provide a virtual address, MMU gives you a physical address. That works for traditional operating systems, but with virtual machines, now we have one more level of indirection. Okay, so what that means is that we have the virtual address space for a process that's running inside a VM, and then because it's running inside a VM, and the VM itself has a virtual view of the physical memory, right? So there's this intermediate guest physical address space, or a VM's view of the physical memory. So the virtual address has to be first translated to VM's view of the physical memory through a first level page table. And then the VM's view of the physical memory or of its own address space has to be translated to the actual physical address space through a second level page table. Okay. So now there are 2 page tables involved, the first level and second level page tables. And the first level page table is handled by the guest operating system, the OS inside the VM, whereas the second level page table is handled by the hypervisor, which is assigning physical memory to all the VMs. Okay, so now we have 2 page tables. So the hardware has to support these. The MMU has to understand that there are 2 page tables. So for every virtual address translation, you have to convert it to the guest physical address, and then to physical address. So, so what used to be, one mapping is now a two-level mapping. So this is a big change from the traditional virtual memory that we have learned to going in a virtualized setting. When you have a process running inside a VM, then MMU has to have two levels of page tables. So this is what this is another big feature that was added with Intel's VTX and AMD's AMDV. And in the case of Intel, they again did their own thing. They're two different companies. They're competitors. They don't even want to have the same names. So but effectively they're implementing the same functionality. So so Intel called it two-level page tables, extended page table. So this second level page table that was added for virtual machines, this was called EPT, or extended page table, whereas AMD called it NPT, nested page table. They mean the same thing. There are some minor implementation differences in terms of format and all that, but EPT and NPT mean the same thing: extended page table and nested page table. So now MMU, for every process running inside a VM, there are memory translations goes through two page tables. The regular page table, or the first page table, which is maintained by the guest OS, and then the second level page table, EPT or NPT, which is maintained by the hypervisor, right? And because now we have two page tables, we also need TLBs for each level. Remember when we had a very nice and clean world earlier where we had one page table and then one TLB inside the MMU and everything was very nice, okay? But actually even that's a very simple world, because we saw that when we had super pages, then instead of one TLB, there were many TLBs for different super page sizes, right? So now it gets even more complicated, because now you need TLB for the first level, then you need TLBs for the second level, EPT, NPT, and then for different page sizes, and that introduces complications on what you can and cannot do. Like, what does it mean to have a super page inside a VM, right? So, and I won't go into the details of that right now, but again, there are a whole lot of architecture-specific limitations that come into play when we do something like that. And hypervisor has to be more complicated to handle these details, okay? Any questions so far? I hope this is clear. If not, it's a good time to ask. The notion of having two levels of virtual address translation versus the traditional one level of virtual address translation. So this is an important concept to understand. There is one of the details that I didn't cover here, this a strange thing called shadow page table. So what this is like before Intel and AMD, they got their act together and came with the hardware extensions. People had only the single level world. The CPUs and the MMU used to understand only a single level page table, right? But companies like VMware and Zen, Citrix, they wanted to run virtual machines that needed two levels of page table. So people wanted to do two-level page table translations, but they actually had only one page table recognized by the hardware. So what do? Well, they said, okay, we'll pretend that we will have two levels of page tables, first level and second level, but this is all entirely fictitious, these two page tables. So whenever we run a process inside a VM, then what we will do is the hypervisor would take these two levels of the page tables and combine them together, right? So the hypervisor says for every virtual page number, what's the guest physical page number and what is the physical page number? So once you have a virtual to physical page number mapping, you would stick it inside another page table called a shadow page table. and the shadow page table will be the real page table. So it's kind of a compressed view of the first level and second level page table. So upon every context switch, you can imagine that whenever a process is scheduled in a VM, the hypervisor would then go ahead and update the shadow page table for that process, and then tell the MMU that this shadow page table is your page table that you need to use. Okay, where the shadow page table will have the virtual page number to physical page number mapping, and it would skip that intermediate level because that computation has already been done in software ahead of time. So what that meant was that upon every context switch, even if you're switching from one process in a VM to another process within the same VM, you have to, the hypervisor would have to get involved and it would have to construct the shadow page table for the process, for the new process. So it was very computationally intensive. It was a high overhead mechanism. There were many optimizations to make the shadow page table construction cheaper. And of course, getting it correct was very hard. And that was another reason why Intel and AMD came up with their hardware extensions. So once they came up with their hardware extensions, there was no need to construct shadow page table. All you would do is tell the MMU, here's the first level page table, here's the second level page table, go figure out the translation yourself. Okay, so the hypervisor had less work to do and there was less chances of things going wrong. Okay, does that make sense? Any questions so far? Okay, so next we will briefly look at I/O virtualization. So remember there's CPU, memory, and I/O. All right, I/O devices like things like your hard disk, network card, and for virtual machines, we want to give them a view that, for example, they have a virtual hard disk or a virtual network interface card, right? And hopefully this will behave just like a physical network interface card or physical hard disk. So how do you do that? There are many ways of doing that, but so there's again a trade-off between what technique you choose depends upon whether you want transparency or whether you want performance. Okay, what does that mean? So for transparency means that you don't want the VM to realize that it's really running in a VM. You don't want the OS and its applications to realize that they are running in this VM. So what that means is if you're providing a hardware device to the VM, it should look just like a physical hardware device. For example, let's say you buy a Broadcom network interface card or a Seagate hard disk. Okay, so they should look like a Broadcom network interface card or a Seagate hard disk to the VM, just down to the low level control operations, registers, device drivers, and so on. So if you did that, then you don't need any special device drivers. You could just use existing device drivers in the guest OS and have them talk to this virtual hardware as if they're talking to the real hardware, right? But it's nice in theory, but in practice, it's very hard because there are thousands and thousands of hardware devices out there with their own device drivers. And in order to provide a virtual device for every physical hardware device out there, it is a Herculean task, right? And many of these hardware devices are not easy to virtualize. There are some devices that are easy to virtualize, but most of them out there are not easy to virtualize. You can't do a trap and emulate operation on the I/O instructions for each and every physical device out there from every make and model from every vendor. So, typically, and also they tend to be very slow. Even if you can emulate it, the I/O throughput you will get is very, very slow. So device emulation would be nice to have, but in practice, it is too slow and too hard and almost impossible for majority of physical devices. So the second option is to use something called ParaVirtual Devices. When we talked about para-virtualization in the previous class, we said that we could modify the guest OS a little bit to make it aware there's a hypervisor there, which is providing it virtual resources. And this approach makes a lot of sense. We are sacrificing the transparency part to get better performance. Okay, so this makes a lot of sense for IO devices. So ParaVirtual Devices means that we insert special device drivers inside the guest OS that tell the guest OS, hey, you have a special virtual network card or a virtual hardware device. And the guest OS that way knows that it doesn't behave like a typical physical network card or a physical hardware device, right? So these are called ParaVirtual IO devices, and they can be much simpler. They're just, so guest OS knows these are software representations of an IO device. Communicating with these ParaVirtual devices is much simpler, and emulating the IO operation on these devices is much more easier. So and they're more portable, meaning that you can have any physical device, any physical hard disk, any physical network card, whatever. But then these ParaVirtual devices can be the same. So you can take any ParaVirtual device and use it with any physical device. So it gives you more portability, right? You don't have to keep reconfiguring your VM for different types of hardware devices. So this is the most common way of accessing IO operations in a VM. And most likely the VMs that you're using, not most likely, almost certainly the VMs that you're using for your assignments, they have ParaVirtual. So if you log into your VM and check the disk or the network interface, it would be some kind of a ParaVirtualized IO device. Now, people should be happy with that, but unfortunately they're not, because the performance of ParaVirtual IO devices is still not that great. Because let's say you're sending a packet out on the network interface from a VM, it has to first go to this ParaVirtual device. From there, the hypervisor has to pick it up, and then the hypervisor has to then send it down to the physical network interface from where it will go out. And likewise for receiving, the hypervisor receives the packet first, then it sends it to the ParaVirtual device from where the guest OS picks it up, and so on. So hypervisor is in the data path for both input and output operations. And that adds extra overhead. If you want very high throughput or low latency, then this doesn't work too well. So another increasingly common model is something called direct device access. So if you really want high performance, highest possible performance from your IO device, then what you do is when you create a VM, you assign it a dedicated hardware device. So for example, there may be a dedicated network interface or dedicated hard disk, and you can assign the whole thing to a VM saying this is yours. So you can do whatever you want with it. But that's not easy to do. I mean, in the sense, it's not easy to do in a safe manner because IO devices do DMA operations. For example, the physical disk can do DMA operation to some part of the memory, right? So if a VM is allowed to tell your physical device, you do DMA operation to some part of the physical memory, that's not safe. You might do a DMA to some other VM's memory, which is actually a security hole, right? So to prevent this type of security vulnerabilities, Intel and AMD again, there's this notion of IO MMU. Just like for main memory, there is MMU. For physical IO devices now, there is IO MMU support. What that means is that the hypervisor has the ability to restrict which parts of physical memory a given IO device can access. It can do DMA operations. Earlier, it wasn't there. This protection wasn't there. So a physical device could access pretty much any part of the physical memory. But now, with IO MMU, you can do this restriction. You can set up a restriction in place. So one VM doesn't do a DMA operation to another, set up a DMA operation to another VM's memory. So this IO MMU, along with the direct device access support, this is called VTD, virtualization technology for directed IO. And so this is a hardware support built in. So when you buy a CPU, it usually comes now with VTX and VTD, and of course you have to enable them to use them with VMs. But once you use them, then you can get dedicated I/O devices for VMs with full I/O performance. Okay, so but also it's less portable because now once you have a dedicated hardware access for VM, then then the VM needs to have those corresponding device drivers in order to use those devices, which affects things like live migration. Okay, any questions so far?